Now we're ready to talk about how to integrate over a surface S, where S is given as a parameterized function of two parameters that live in some region D. So here's how we write the surface integral of a scalar function f. We write it as the double integral over S of f ds. So how could we compute this, or what does it mean? Well, based on what we observed last time, we can write that ds has a magnitude of Ru cross Rv times dA, where dA is in the sense of du dv. So that means that for practical purposes, the integral of f ds is really an integral over u and v, living in the region D, of this quantity magnitude of the cross product of the partials. Now if we have a vector field, capital F, we can proceed just like we did with the line integrals and define a scalar function based on it, which is the dot product between the vector field and n, where n is now a unit normal vector to the surface. So before, with a line integral, we added up dot products of f with a tangent vector. Now we're doing f with the normal to the surface. And this is a quantity which is called flux. It's an amount of stuff that flows through the surface per unit time. So now we can write the surface integral of f dot n ds. And just as happened before with the line integrals, the nasty vector magnitude actually cancels out. And so we get this cleaner form for the dot product here. And then as a notational tool, these quantities together we now call the differential ds for the vector ds. And so now the surface integral of the vector field is the dot product of f with that vector surface element ds. What ds represents is it has a normal direction to the surface, and its magnitude is the area of a small patch of the surface. One final note, in the integrand, if we set f equal to 1 everywhere, then the integral of ds over s is just the surface area of s.